particular moment by my watch in Pacific, on the Pacific coast, it is 1:38, but let's make it generously 1:40. Would it be reasonable to say that we regroup at 2025, 2:15? No, 2:25. 2:25. All right, guys. So let's regroup here exactly at 2:25. And we mean it, guys. Because we have a long territory to cover, have a quick lunch and let's make progress after that. Give people to recap, till now we have done bar charts, or we have done scatter plots, each of these, and we have done line plots. And we started with one-liners in each of them. And we ended up with a sort of a milestone or a landmark visualization that we could reproduce. In the case of bar plot, we did the Two Roses of Florence Nightingale. In the case of scatter plot, we did the Gapminder's famous visualization on the wealth of nations and so forth. And when it came to the line plot, we ultimately ended up with the famous stripe plot, which is used for, which has become iconic for climate change and the climate change conference, global climate change conference. So in the same spirit, now let us move forward. But before I move forward to other big visualizations, I would like to take a pause. I gave a talk during the week on kernel density estimators. Now, the audience was very small, and there was a request that this is important enough that I repeat it for everyone. So this is a repetition now for everyone. I'm going to bring up that visualization. If you have been through this, if you were in that midweek session, then this could be a refresher, or this could be a time to go get a half-an-hour nap. So without further ado, let's get started. I hope, are you able to see my screen, or have I not shared my screen yet?
Not shared.
Okay. So let me give you the big picture here. See, suppose you look at data. Let's look at one-dimensional data, the weight of ducks or something like that, weight of animals, birds. You realize that when you look at a continuous variable, you can have any value possible within reason. For example, the height of any two people could be off by millimeters or even low, right? So you have a continuum of value for all practical purposes. You do have a range. For example, you don't tend to find 10-foot people. You don't tend to find a 1-inch people, right? You don't have Thumbelinas, and you don't have those giants that Gulliver Travels speaks of, right? But in between, you have a pretty large variety of heights and weights of people. Then, if you had to guess, how is the weight distributed? It gives you some intuition. What is how likely is certain value to be present? For example, you would say that, that if you're looking at children or in high school, their height and weight distribution would be one way. If you're looking at, let's say, sumo wrestlers, their weight distribution would look entirely different. The likely weights are quite different. So today we will talk about this topic of probability density. Probability density is at that particular value, how likely is that value compared to other values? Normalized to 1, it is integration of a density function should be 1. That's a basic intuition. So we will develop that intuition today through a notebook. It is one of the visualizations that people miss. So the main thesis that we are going to make today is that histograms are good, but histograms are flawed. They are sort of a basic way of understanding the likelihoods of things, and they are better estimators. From data we can infer or build better models of how the data is distributed, what the probability density distribution is. So to motivate that, what I would like to do is take this particular example. In this example, look at this picture here. I just took a picture from the web. This is from the Unsplash website, credited to the photographer, Jonathan Pinette. And I felt this is This could be the pond behind your house. This could be, I don't know, is this Lake Elizabeth like that? Probably, right? Or we have in our neighborhood, Lake Elizabeth, a scene from Lake Elizabeth. There's anything, it is pretty ubiquitous scenes like this. Whenever you see local water bodies, you often find ducks in there, you find geese in there. So look at this picture, and if you say, what can I infer about the populations of birds and geese? How likely am I to find them in the water? What would you do? You would say, all right, let's do one thing. Let's count the ducks, how many ducks there are. And if you count it carefully, you would probably come to 11, unless my eyes miss something. I counted 11. And then if you count the geese, you will find that there are 4 geese, right? These 4 geese. The geese are big white. Ducks are tiny little birds, smaller birds. So you could say that, all right, let's represent this data visually. You could say that we are creating a data frame in which literally there are 2 columns. That, I mean, we might as well show this data. Let me do this. Keep running it. And this is the data. And this data might as well show it later. There we go. So it's as simple a data set as we can have looking at this picture. I hope you would agree. There are 11 ducks I counted, 4 goose. Right? So 4 geese. Now,
can you zoom little? Can you zoom your screen little?
In the picture or the
code? The code actually.
The code.
Yeah.
Do you want us to go type with you, or is this something we just want to discuss right now?
No, this one I don't want you to type. This will move a little fast because it is a core topic. I want you to get familiar with it. Let me see, do I want you guys to type? Not this one, but when we go to more interesting examples, then I will expect you to type. So
okay, thank you.
This is a motivating example. Just read and understand. I hope when you look at this code, there are no surprises. Right, here it is. So without further things, you know what I would do? I would like to produce a count plot, right, and a bar plot. 1 bar for ducks, 1 bar for geese, right, in which I count the frequency or the count plot of this thing. Now remember, what we are looking at is the species of the bird and their counts. All the usual cosmetic, aesthetic elements, sorry, that we apply, we will apply. At the end of it, what we can do is we can use the SNS bar plot, C1's bar plot. I just happened to choose that. Why did I choose C1? For no particular reason, because here I want to focus on bringing out the idea. I could have used Plotly, Altair, Plotly, any one of these. I randomly picked C1, and it's quite common. Bar plot actually in C1 is perhaps the most straightforward. Let's look at this thing. We are used to bar plots. So you would agree that this is, by now, if you have reviewed the Jupyter notebooks of last week, this is a no-brainer. You create a bar plot, X is count. I made it horizontal, just in keeping with what we did last week. Y is species. So I get this, this particular bar plot. Right? Does this make sense, guys? At the bottom is the count, how many? There are 11 ducks and there are 4 geese. Quite a simple data set and quite a simple visualization of it. Then suppose I ask this thing now we do modeling. I tell you that the world is filled with many ponds and huge number of ducks and geese, practically uncountably large number of ducks and geese in the world, and there are probably uncountable counts ponds out there, right? Or ponds or lakes or whatever. So now, if I were to ask you, if this data, if this picture is representative, right? If this is representative of what's happening all around the world, and we consider this, in other words, if we consider the birds that we see here in water to be a sample of a larger population reality. Now, we can't go and look at all the ponds of the world, all the geese, all the ducks, and come up with the actual ratio. What is the probability of finding a bird in the water to be either duck or a geese? Right? If you had only 2 choices, you would like to know the probability of that. So what is the best you can do? You can say, hey, you know what? at this moment, this is the data. If this data truly, and this is the word we have to remember, that data is always a sample from a population, not always, but quite often. You don't know the population. It's a basic statistical fact. The population is, for many more situations, it's not practical to go and grab the whole population. For example, if I ask you, make a histogram or something like that, a probability that people are a certain height, let's say between 5 feet and 5 feet 1 inch or something like that, you would say, all right, very simple. Let's take 7.5 billion human beings, line them up and measure them. That is the population, but that's not very practical. So what can you do? You can draw random samples, representative samples, and that itself is an art. It's a science of how do you draw good samples so that you don't have biases. Because if you go and draw 5 little kids, your understanding of the height would be completely wrong. Because there's a bias in the data. If you likewise, if you pick a few basketball players, your understanding of height of human beings would be again very biased towards the high values. So you have to take representative samples. Right? People often use the word independent and identically distributed. That is, you pick a sample, it has nothing to do with the previous sample that you picked. And it should be identically distributed, means it should be randomly, truly randomly picked from the population. And if you try to get, so this word IID, you find quite often in data science and statistics, independent and identically distributed, but more broadly, and then it's related to the topic of essentially representative data of the population. But suppose this is it. What can you tell, given this distribution? How would you make a probabilistic guess? I ask you, what is it telling you? What's the probability of a bird being a duck as opposed to a goose? You would say, well, that's easy. I will take these ducks, there are 11 ducks out of 15. So I will say 11 out of 15, 11 over 15. Would that be a reasonable statement to say? Yes. Right. So we do that. And that makes it into, so that's what I do. In this code, no surprises. I just divide it by the total. It's a simple data set. But now when I do that, now what happens? The x-axis becomes the probability. Since there are only two things, you say that this is this probability and this is this probability, whichever those values are, and they add up, of course, to 1. Now, people, I may say that these are probability, right? Now, for discrete variables, it is okay. You say that what I have is a probability mass distribution. I'm saying that 75 or whatever percent happens to be ducks, and whatever this comes out to be, 26, 27% happen to be geese, right? It's a discrete distribution. That's why people often use the word probability mass functions. I will generalize it now. Now let's go to continuous variable. So I'm creating a data set, this data set. And this part, I would like you to do with me. Let's go and this part, you don't need to be able to type it. It is just my way of generating a data set, which I know about, right? So let's go and, where is it? I will post it to, or could somebody help me post to,
Do you want me to do code posting?
yes, that would be awesome. So I posted the first element, guys. Just run this. Remember, at the top of your notebook, don't forget to do this. These two things, visualization imports, whatever it is. Run the visualization import. It will automatically bring in the styles. And because I didn't feel like cluttering the top of the notebook with lots of imports. So do that and then do this, right? Very much like in your previous note. Once you do this, now let's look at it. The first thing you could do, and remember our topic here is to understand the probability density distribution, right? That is the core topic. Why is that valuable? You will see why it is a valuable visualization to have about data. It says a lot about data. So The earliest work in this space was done by the great statistician Pearson, who was a student of Galton. We're talking about 18 somethings, long ago, right? A very, very long time ago, almost 200, 150 years ago. He came up with a method. He says, take the histogram and just divide it by the total, which is what we did just now. He said, suppose you have a continuous variable, discretize it, like make it into sub-regions. Suppose your range is from 1 to 100, discretize it into sub-ranges from 1 to 10, 10 to 20, 20 to 30, and so forth, and you will get 10 different bins, right? Once you have discretized, you have bin, so then you do the binning of the data. You take the data and you ask this data point, this datum, which particular bin this datum falls into. Whichever bin it falls into, put it there. Imagine that you're putting a bit of material there. And here is one basic intuition. Imagine you're putting 1 unit of sand in that particular bin. And think of each bin as a glass column. Right? It's a column of glass into which, or cylinder of glass into which you can drop a 1 unit of sand. So what will happen? Ranges or bins where lots of values are falling, that column will start rising. Would you agree? As more and more data instances you encounter and you start ascribing it to the bins, some bins will rise up in height faster than others. So that is the counting part. Then what happens is that you can count all of these, and then all you need to do is, suppose you divide it by the total. If you divide it by the total, what will you get? You will get the same probability distribution that we are talking about. So now to do that, this is the code I want you to write. You just became familiar with histogram before lunch. Remember, we talked about density is equal to true. It does it for you. So the only crucial line of code is histogram data. You can even decide how many bins there are. Here I've arbitrarily decided 100 bins. I've said density is equal to true, and the rest of it is aesthetics. All of these are aesthetic elements.
Want me to copy that to Slack?
Yes, Kate, your voice is coming out very faint.
Oh,
But yes, if you could, this bit of code, I would rather that we did, no, don't paste this one. Folks, can you please type this in quickly and to your own satisfaction be able to reproduce this plot? I'll wait a minute.
okay.
Are we all done? Or should I wait a little bit?
Could you wait a little bit, please?
So do you want me to paste it?
No, don't help me.
Okay.
This one I want people to actually do it. By the way, some of these are aesthetic elements. If you so choose, you can skip it. Like for example, in the tight layout, I put 1.05. It is just to add a little bit of white space when you are trying to publish it into a book. And some of you know I'm trying to write my own data science book, and some of these visualizations quite literally will go in there. Avanti, can we move forward? Anyone else who's waiting? Or who's still typing?
Yes, you can go ahead.
Okay, guys. So you should get a plot like this, which looks aesthetically pleasing and all that. So we took 100 bins. And we saw this. What can you tell? Now think about it. What is it trying to tell you about the data? It's telling you that quite likely there's a peak here and there's a peak of probability here. Okay? These are the most probable values, right? So if you look at it, for example, as the weight of the negative values, so give me a little bit of a license. Weights are not negative, but suppose I have two species of birds, ducks and geese. Maybe this is the spread of the weight of ducks. This is the spread of weight of the geese. I don't know. This may be completely unrealistic from a biological perspective in some units, let's say. And of course, negative values are unlikely. But think of whatever it is, maybe temperature. We are looking at temperature in two different regions of the world, activities, and mixed up data. So you get something like that. How do we now? You notice that we said normalized probability densities, normalized. Typically, histograms are unnormalized. Most people don't do that. So I just want to reiterate the point that by default histogram, the y-axis is count. It's not probability density, but we can repurpose it for probability density by simply saying density is equal to true. Right? So now here the y-axis is probability density here, as opposed to it. So you can remove that density is equal to true, and you will then get another plot. And I won't let you, don't have to spend time doing it. But you can take me on trust that this is what you'll get. Now, there is histograms are ubiquitous. All the books on data science, they bring in the histogram quite early on as a good descriptor of univariate statistics, right? Or one variable. Univariate is one variable. A statistic means a property of that. So mathematical property of the data. Something that says about the data. So now the problem with histograms is it is too sensitive. The shape of this is too sensitive to the choice of the number of bits. How many bins should we take? There's a bit of scholarship on what is the optimal number of bins, so on and so forth. If you want, we can chase it out. People have talked and have comments and things about it. My own feeling is it's not really worth chasing those directions. Maybe a little bit worth it, but okay. Now what I will do is I will take this histogram, and I have made, and this one you don't need to copy, you can take me on trust. What I have done is I've made 3 plots, exactly the same code, but I have taken it for 3 different values of bins, number of bins. So here I go. I'm making 1 row, 3 columns, isn't it? And I'm saying share the y-axis. Now, do you notice that what am I doing with axis 1, axis 2, and so forth? These are the subplots. The first subplot, I'm saying make a histogram in which the number of bins, right? I didn't even specify. I left it as a default value. In the second one, I'm saying, okay, number of bins is 50. And the same code, exactly the same code, I say now the number of bins is 500. When you do that, what you notice is you see this. You see that these things look different, right? In fact, because here we have a lot of data, we have 17,000 data points, you begin to see the emergence of the real pattern. Your mind is already beginning to see a pattern. You know that this rise and fall, this very jittery or spikes, they're not real. In your mind, you already start building a smooth curve of a probability density distribution, isn't it? Your mind now, through any one of these curves, you realize that, first of all, the probability density doesn't change radically. It has to be a smooth function. The weight of one, likelihood of the weight here, and just slightly adjacent, they can't be vastly different. That is unrealistic. These are the main problems with histogram. They are very sensitive to the number of bins, which becomes a hyperparameter. Secondly, they're unrealistic because you know that the underlying probability density has to be a smooth curve, isn't it? It can't radically change with a slight change in the weight of a bird or something like that. Right? It can't become so unlikely. Discrete jumps are not possible. It has to be smooth. if we agree with that, and this line of code, I hope now, guys, I won't give it. Let me give it to you so you can play around with it. Or yeah, could you please, who's Kate or Harry? Could you please paste it for everyone?
Sure.
Oh, you already did. Thank you. So you do that, repeat it so that in your notebook you have this. And now you ask this question that, all right, these are the limitations of the histogram. What can we do? Let's think from first principles. Suppose you found a bird whose weight is, let's say, 5 pounds. What exactly 5.0 pounds? What exactly can you say about the likelihood of getting birds? What is that data trying to tell you? Surely it is not saying that all birds are 5 pounds, right? Would you agree? If you just have one data point, you would surely say that no, that's not possible. If nothing else, there are instrumentation errors, there are errors in the measurement process and so forth. So the values are probably clustered around 5 pounds, isn't it? So you would say there is somewhat 5 pounds is likely, maybe it could be 4.9, maybe it could be 5.1, and maybe less likely it could be 4 pounds and 6 pounds and so forth. And you sort of decrease from that particular value. So here is one intuition you can take a bucket of sand, 1 unit of sand. Are we together? And you say, if I find a value of 5 pounds, I can go to the x-axis on 5 and pour some sand there. Now, how I pour sand is the crux of how we do it. There are multiple ways of doing it. If you think in terms of the sand analogy, you could have divided the x-axis into discrete bins and then put all the sand in that particular bin, right? Which was the histogram way of looking at it. But now let's generalize. Suppose you take your sand and make it into a square, right? One square or something like that. And wherever you find the data, you put it there. Means it is equally likely to be there and within a neighborhood of it, but after that, it's 0. Unlikely to be anywhere near after that. Now, that looks unrealistic, of course, but it is an approach that you can take. It is at least better than histogram binning because you are centering the data on centering your square of sand onto the main point, the actual 5 pounds, not putting it. So suppose you have a bin that goes from 4.2 to 5.1. You're putting sand and it looks as though it's more centered around 4.5 or 4.6 rather than 5 point, exactly 5 points. Right? We have an improvement here, made the block sit on top of 5. That particular way of doing it is called the top hat, right? And this putting sand and the shape of the sand that you put for each data point, the word people use is, it's the kernel, right? It's a kernel function or kernel density estimator. You're saying that each data point, the narrative it is telling you is that this is how the probability is shaped in the neighborhood or thereabouts, or in the neighborhood of that point. Are we all getting the intuition? Right? So now if you think like that, that is more realistic. And now we have introduced the concept of a kernel, right? So we can say, let me put it now in a slightly more mathematical way. We say that each point xi, now it says that in the neighborhood, so if you take up any other point x, the likelihood of finding the data there, we can say depends on the distance from that point in some way, right? Then there is a hyperparameter here. We'll talk about it in a moment. It is like, and it is called the bandwidth parameter, which we'll introduce. Ignore it for a moment. This pouring of sand is called the kernel density estimator, right? It's a fancy word, but if you think of a unit of sand poured there, that's what it is. Now, when you pour sand, you could pour your sand very peaked, right? If you're making a hill, your hill could be really peaked. It could be like a fort, like literally square, or it could be smoothly rising up and falling down. If it is smoothly rising up and falling down, you could be generous. You could spread it, like you could not make it so high, but you could make it spread out more, or you could sort of collect much of the sand near the point, make it much more peaked, right? Go higher, but very easily not spread it far, right? You realize that you have a choice of that. So that is what that bandwidth parameter H is about. It's about how tightly you have packed the sand or how much you're letting it sort of flow in the neighborhood of that, wider neighborhood of that, right? Or how much you're keeping it, like how much are you respecting immediate neighborhood versus slightly outward neighborhood versus far neighborhood. Right? So one could be very generously you spread it far, but then at that point the probability just barely peaks a little bit. Right? Density peaks a little bit. So that is it. So now let's create, what we will do is we will create this function. I call it delta, which is the scale distance. Distance from the point divided by H. So one of the most popular ways that you would probably want to put your sand, if you think in your mind, I'm pouring sand, would you probably pour sand like this symmetrically? Yes, something like that. So this is a pretty good guess for a kernel function. By the way, at this, there are no wrong answers. The only thing has to be that kernel function must be positive. It must be symmetric around that point. And the area under the curve, of course, has to be 1, because the probability of finding that kind, what that point is saying is that the probability of finding it is thereabouts, summing up to 1, right? So you would agree, and you can create many such functions. Perhaps the most ubiquitous is, of course, the Gaussian kernel. Those of you who did machine learning courses past with me are familiar with it, how we use Gaussian kernels. They're great. So we use this. Now, what do we do? Let's take the Gaussian kernel. Right? And this is, by the way, just showing how a Gaussian kernel works. Here, but there are quite a few kernels. I've just itemized exponential kernel, cosine, top hat, Lipa-Neschikov. Now, one of the, which is basically sine wave. Then there is a tricubic and bicubic and whatnot. Anything goes so long as it has the right properties, right? And I didn't have the time, otherwise I would have shown you how each of those kernels look. But if you, I think it's there. And now comes the question. Well, your data set is not made up of one point. It's made up of many points. So every time you see a new data point, wherever it is, you say, oh, the values are likely to be here. And you pour a bucket of sand. Another point, you go and pour a bucket of sand. So soon what will happen? You'll have little sand hills all over the place. Would you agree? Along the axis, you'll have created multiple sand hills. Are we together in the intuition so far? Right?
Yes,
And
sir.
so now we ask this question, collectively, what is this data set? What is the probability saying? Now we have a little bit of a problem. All of those individual kernels, their probability densities by integrating to 1. So suppose I have D data points, right? Suppose I have a data set D whose cardinality is, this is standard mathematical jargon. You put 2 parallel bars to say how many points are there in that data set. So suppose there are 100 points. When you do the probability of curve, the density estimation, you want to say, add up all of these things. So at any given point, how much so here's the thing. So let me put it, let me draw it out, guys. What we're doing is, give me a moment. So let's go with the intuition here. Suppose I have this value axis. I come across a data point here. And so what I do is I go and put a little sandhill here. Right? I find another data point somewhere here. And I put a sandhill here. Oh, sorry, blue for sandhills. So let me put a sandhill here. Let's say that I find another data point and put a sandhill here. I find another data point here and I put a sandhill centered around this, right? And so I keep going on and on and on. Let's say that I find another data point here and I put a sandhill. I create a sandhill here. Oh, sorry, this is off. Let me make it this for this. The point would be somewhere here. And suppose, oops, sorry, sandhill here. And you guys are getting the idea, right? Suppose I find another data point here. And so I put a sandhill here, right? At this point. And suppose, let me keep making some points here. to see what's happening. So let me go and create sandhills for each of them. What are these sandhills called in the formal language? What are each of these sandhills called in mathematical terms? Kernels, isn't it? So suppose this is xi. So this is a kernel function xi, right, given some hyperparameter, some bandwidth h, which the bandwidth h controls the spread of the sandwich. Are we together, guys? So now it's a hyperparameter. It's up to you. And it's, you know, in machine learning, you never can get away with hyperparameters, right? So we'll come to that in a bit. So now comes this question. I asked this thing, what are all of these points saying about the probability of finding a value? Let me say here, this is my sample point. You know that each of these sandhills and all of these sandhills, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all of these 10 sandhills will contribute some little probability here. So I will get a K1 plus K2 plus K10, isn't it? All of them are saying, I say the probability is this much at this point. Would you agree? Right? The trouble is, this value you can't take because it's not normalized. So what you have to do is you have to take all the answers and divide it by 10. Would you agree? To get the actual probability x given h.
Yes.
Right? And that is probability density estimation. And just ponder over it for a moment. This is far better way of coming up with a probability density estimate than using a histogram. Would you agree? Right. Here you can pick what are the choices you have. You can pick a reasonable kernel function. You can pick a bandwidth parameter. Bandwidth is the hyperparameter. There's two hyperparameters. Which kernel did you pick? Which this thing. Now, generally, what is happening is, so long as you take smooth, continuous kernels, right, not with sharp edges, generally, most of these kernels, they yield practically the same result, right? Very close to each other, they give you results. Gaussian kernel is by far the most popular. You can pick it, right? Or you can pick another kernel and so forth. Right? And in the language of kernels, you would say more popular than Gaussian is that binning kernel, right? Which is the histogram. But we just realized that it's not a good idea to do that. So what happens is when you do all of this, you will get, would you agree that the sum total of this would be that you'll get a curve that probably looks like something like this. Well, forgive my drawing, but this is how the px function would look. The cumulative, well, you know, it should have peaked here, but I've made it peak somewhere else. Forgive me, let me redraw it. And then rewrite it as 10 divided by 10. Let me make it peak here. Okay, better. This is your probability function. So that is the intuition. Let's use that intuition and see what happens. We go back to our Jupyter notebook.
Can you stop over there one?
Yes.
So you're saying that this cumulative one,
Yes.
the shape of it will look like the small baby's insect.
Will be influenced. It is the additive model.
Correct.
It adds up.
But will it look like that, or what will it look like?
Oh, you don't know. It need not even look like a Gaussian, basically. It will look differently. It will certainly not look like a Gaussian. It will look like whatever the data distribution truly is.
Okay.
Yeah.
So you said that, maybe I didn't misheard you. You said that even if you take different types of these curves, in the end, they will all look kind of similar.
Yeah,
So
with
you're
sufficiently many values, they will all look pretty close to each other.
So you're saying that if you take Gaussian or any of those, one of those four things you said,
Yeah,
the end result of that summation, the shape that
pretty
will
much.
look, they will look same irrespective of what spread you take.
That is right. That is right, except for the hyperparameter. So for example, you could take something like this, right? This is your cosine kernel, right?
Okay.
So what happens is now you're building things like this, right? This kind of thing. And so ultimately, sorry, this line shouldn't have existed where the point is. So you can play around with it, but eventually the shape that arises will be very close. So general feeling is that while you can change your kernels and see the changes in result, if you have sufficiently many data points, generally not worth trying to optimize with the best. One of the things is the sine wave, the sine kernel, the Russian name I never can get properly. Ipanichko, yeah, that's right, this guy. Ipanechnikov, right, tends to, in general, outperform others. But I prefer, I just go with the Gaussian and be done with it, right? But there is a problem here, like all machine learning situations, there is a hyperparameter in the model. How generously did you spread out, or did you pick your kernels, right? That is the bandwidth parameter. So what I show here.
So I'm trying to understand again, kind of little bit. Say, suppose you had wild chicken, right? Which kind of fed in the wild and things like that. And you brought all the small chicken babies together, their spread would be quite different. On the other hand, if you had farm chicken and you fed them exactly measured thing, they would probably have, they will all be growing up at the same rate and things like that. They will have this kind of a separation. There'll be a weak ones, but you give antibiotics, make sure that their weight and all will.
You could do that. You could, for each group, you could pretty much actually apply a different kernel.
So is that the reason why you have differentiate?
No. The thing is that in the industry, like, see, once you agree on the theoretical principle, there is no way we can say which is the best kernel. Okay. There is no way. So everybody will try a different kernel. Okay, that's all it is.
But because it's not representative of any way what the underlying data is. That's what I'm thinking.
It is, because see, it's a hyperparameter of the model which kernel you choose, and in a way, data will tell you that this was the best kernel. Okay. Right? It becomes a hyperparameter. So how do you know what is the right hyperparameter? Data rules, data speaks.
You're taking average. You're taking average of the data automatically happening back.
So now what happens is, so this is the explanation of this little bit of mathematics. I hope this mathematics looks, it is just, think of it as a cryptic mantra. I mean, if this looks scary, it's basically we're talking about the buckets of sand we are pouring all over the place. Now, the problem with this obviously remains that it is sensitive to the hyperparameter bandwidth. In this case, if we take a Gaussian kernel, we have a bandwidth parameter. So what I have done is I put a bit of code here, and we can just paste it for you so you can reproduce it. What it shows is how does the kernel change, just the kernel, a change for different values of the hyperparameter. So you notice that this is very simple. If you keep the kernel very tight, this is the shape of the kernels for bandwidth. This is a very tight hill. You're saying the value is exactly 0 or very close to it. The next one you're saying, well, the value is around 0 or even up to 510 is pretty likely. And then you get more and more relaxed about how the values are spread around that particular 0, isn't it? Right? So this is how generously, this is the meaning of the band, how far you're willing to spread the data. Right? And let's go now. Oh, I should have done something. One second, let me do this. I don't know if I have run the previous cells and it will have an effect. Let me do this. Share y is equal to because I've not run the previous cells, I'm not sure whether this is done or not. So now, share, oops, sorry, comma. Yeah. So, well, of course, do you notice that when you keep the bandwidth very low, you get a high peak, right? The hill is high because the sand has to go somewhere. It rises up. Then as you relax make your bandwidth bigger and bigger, your hill begins to get more spread out, isn't it? So that is what I was trying to illustrate. You can see the spreading out of the hill and the height has gone down. Now, let me plot the same kernel. All of this, actually, let me remove the share y because for some reasons, let me just, so, oops, sorry. Why am I? Okay, so this is, let me keep, for whatever reason, I have to fix the size and bit of it. Now, let's look at this same thing. I just plotted it out more beautifully, with filled in the colors. Do you see how the 4 different kernels behave for 4 different values of the bandwidth? You can literally see one. So if you think of it as children playing with sand, one child has spread the sand pretty far and wide. Another child has peaked it, and other child, and there are people in between on how much they believe it should be spread. So now that you have the kernel, one of the questions is, how do you compute the kernel density estimation? So here the word is slightly abused. What we are computing is kernel density estimation of the whole data set, what I'm calling the PX, the probability density, right? Using the kernel method. So people often use the word kernel density of the entire data set. But remember, kernels are the individual things. But anyway, be as it may be, this part of the code I want you to do. So please, because there's a bit of learning here, let's compute the kernels. Use this bit of code, type it in. Actually, I will make it a little bit smaller so that it's readable. Is it readable enough? Can you guys please do this? So this is computing the kernel. It is one of those, I feel that this is one of those features that is rather underutilized when people do data analysis or data science. So I want you folks to learn it, because kernel density visualization, in my view, is one of the strongest intuition you get into the data. You should never skip it. So please do copy these 2 cells as is. And I want you to type it in, tedious as it looks. Oh, the first part Harini has already pasted. So the first part you can take from there, and the second part you can fill it in. This is the first time you're encountering the fill function, so it's worth typing the second part out. So what, unlike a curve, unlike a line, the fill will make an area plot out of it. So it will do this. Let me make it a little bit smaller. Sorry for the fact that I'm jumping around. You notice that this visualization is what we are creating with fill, not just the line.
Do you want us to type this plt.fill this cell?
Yes, please do that.
Okay.
Because this is your first encounter with the fill function. Are we all done, folks?
No.
Okay.
Sorry.
Let's wait.
Also, we're missing that original first data loading part. I don't know, the file or something like that.
Oh, there is a code that you'll find on Slack that we pasted. Look at this, where we generate the data. 1 second. It's a little bit up. Shape of this. Yeah. Here, I will paste. Put it on Slack all over again.
Thank you.
There we go. This is how you generated the data.
Random.
So let me know, guys, when you reach this point. And think about it. Would you rather have this? Do you think this is more informative, or is the histogram more informative?
This
The
one.
kernel plots, yeah.
Certainly, right? And it's also more honest in the sense that it gives you the real intuition into the data. So have we all reached here? Can I move forward?
So the
when you look
kernel
at-
plots, I have a question. So the kernel plots are nothing but a probability distribution, right?
Oh yeah, ultimately they're probability distribution using the kernel functions. That's all.
Okay.
That is why
Thank you.
you see, when people use kernel plots, there's a slight abuse of term. If you want to be really precise, you can say that is the probability distribution that arises when you use kernel density, a kernel estimators, or kernel functions. Right? So kernel density estimator is density estimator using kernels.
Okay.
That's one way to look at it. Then it looks pretty precise. So are we all here so far?
So statistically, what is the difference between Gaussian kernel and normal binomial distribution or any other probability
Normal.
distribution function?
Normal and Gaussian are synonyms. But
Okay.
there are many, it's the mathematical nature. E to the minus x square over 2 sigma square is Gaussian, right? But there's Laplacian, which looks very similar. Log normal can be made if you take the standard, if you take the deviation as 1, it looks actually almost indistinguishable from a Gaussian. So there are many such functions that look very similar. And obviously that goes into things that we'll cover in the mathematics of data science. For example, there are all of these lovely esoteric functions, like a beta distribution, all right? There is a gamma distributions, there is Weibull distribution. In fact, all of reliability engineering has to do with things like Weibull and Gompertz distributions, etc. You take a flight from here to India, that aeroplane goes over the oceans, right?
Yeah.
Crosses what, 10,000 miles or something like that. In the journey, the airplane is made out of what, at least 100,000 parts. And yet you don't worry about the aeroplane popping down into the sea. The only thing you worry about is, I hope I don't get a middle seat. Right?
Yes.
Why are aeroplanes so extremely reliable? Well, it turns out that people have worked out the probability of product failures, each of the component failures. And there are beautiful distributions like the Weibull distribution. Underlying that, in fact, much of that engineering is foundational to these distribution density functions or distributions. So there's a lot of things here. And obviously, this is the visualization course. We won't go into it. But should you take the math of machine learning or the math of data science course, or we deal with those things systematically.
Okay.
So you're saying that maintenance of the brain follows that failure strategy.
Recommendations that come from those probability distributions. So you do preemptive maintenance.
Yeah.
And because of the preemptive maintenance, your aeroplane has become quite literally the safest mode of transport. If you really think about it, your car, etc., they're nowhere close to that. You haven't worked out the equation of everything's failure. Sort of we have reliability. So nowadays these things have computers that will tell you that you need to do oil change. Now you need to change this. At that time, the thing hasn't actually broken, but you have crossed a threshold. Now it will break, right? So you preemptively change it. That's how you get reliability. Somebody once said that you can drive any normal car easily for 500,000 miles. Right?
Yeah.
All you have to do is do preventative maintenance.
Yeah.
That's all. And it just goes on and on and on.
Yeah, and most of the manufacturing things are based on Six Sigma principles, right?
Exactly.
I mean, they are as statistical and it's a normal distribution that they base
use.
everything, the preventative, all the parts that are manufactured are
Yeah.
based on those principles, their quality
That's
and
right.
everything. So that adds up to
That
provide
adds.
you a better.
Absolutely. So the Six Sigma guarantees that when you buy a new thing, it is already very reliable. You know, the reliability will go down as it decays, and there are mathematical models of the risk of the hazard functions of how far it would have decayed, and then you preemptively service it or change the parts,
Right.
so that it always remains at very high Six Sigma reliability, gets preserved almost along the entire lifetime of the vehicle or the machinery. That's how it goes. So that is that, guys. So this looks beautiful. Have you all reached here? I hope you feel this is worth it, guys. One lesson to learn here is always do density, kernel density estimation of your data. Not to do that is practically criminal, right? When you're trying to understand the data, visualize these things. Now, there is a trade-off. Remember that hyperparameter about kernel? Bandwidth. What is the bandwidth and how does it affect? So I wanted to show you, this is a data set that I generated. You notice that what is the bandwidth doing? If you look, and don't worry about the code, which is nothing fancy. I just keep changing the bandwidth from practically 0 because I've rounded it to 2 decimal places. You can't see how small I started. I believe I started from 0.0001. Do you see this bandwidth? And then I go to a bandwidth of 25. Somewhere along this, do you notice that this is too unrealistic, the first one? Would you agree that it cannot be representative of the data? The top one. Then as you flow down and down and down and down, you come to this last one. You realize that this too is not realistic, isn't it? The reality is somewhere in between, and you have to decide what bandwidth you would consider as good. Right? Here, what has happened, it's a high, in the language of machine learning, forgive me for using that language, if you're not doing machine learning yet, this is called high bias situation, right? You have over-smoothed the influences from each point to the kernels. Your hills are too broad, add to it. Here, the hills are too peaked, right? Remember, very small edges like this, very, very peaked ones. So when you take very peaked hills, of course, you'll get a visualization that is like that. And so somewhere in there, so let me just look along the diagonal. If I have to look along this diagonal, at what point do you have smoothness? Smoothness has been achieved. You would say this looks pretty smooth, right? This where my mouse is.
0.6.
Yeah, 0.25 or something. And beyond that, you start losing resolution. Here you see the nice dip, but now the dip begins to go up. This is a place to stop where you achieve smoothness, but you don't lose enough information. So I would say these three are successively losing more information. This is about as good as it gets. Maybe you could argue this is better. I don't know. It is subjective. Maybe this. So somewhere in the vicinity of this, maybe this, maybe this, you can pick. It doesn't matter because the intuition about the data has been conveyed now. Well conveyed, isn't it? So this is how you would do it in first principles, guys. So density estimation is worth doing because knowing the density, you can use it. For example, it's a clustering technique called density-based clustering. DENCLU is literally based off this. We covered that, those of you who did the comprehensive introduction learning and have spilled over to this class. Remember DENCLU. So for example, if I were to tell you where are the data clusters, what would you say? Can you just visually tell where are the data clusters? Where is the centroids? Or where is the, remember the word that we used was attractors, top of the hill of the density function. So can you guys tell me where the two attractors are?
Where the slope of the of this particular curve is 0.
Right, the top, the slope is 0.
Yeah.
So it would be this part, maximums, 1 and 4, isn't it?
Mm-hmm.
Yeah, 1 and 4. So you would say those are the attractors in the density estimate. In the language of clustering and DENCLU, we call them the attractors. And we can use a hill climbing algorithm to get there. Okay, that is about algorithms. Today, it's all about visualization. Now, it turns out that if you use Seaborn, they give you kernel density estimator bit. You don't have to compute it or apply any code. You can just give it the data and it will draw out the kernel densities. So Seaborn makes it a one line. I made it 2 because on one side I've shown you kernel density estimate as a line, and on the second side as an area. And of course, you can mix them, both of them together. Okay. So I made them into 2 figures, 1 row, 2 columns. seconds. And this is doing it. So now we have to move a little fast in the interest of time. We have only 2.5 hours left. So I won't be letting you type it and move forward. By now, I hope you realize that this code is dead simple. Yeah? You don't learn much by writing this code. You already know it. The only thing is to know is that there is a Seaborn has a function called KDE plot. Right. So that now let's go and look at the auto data set. If you remember, we keep coming back to the auto data set. It has miles per gallon, cylinder, displacement, horsepower, weight, and so on and so forth. These are continuous variables. Let's look at the data set. And again, I think that is notebook. You can start by creating normalized histograms. Do you see that after knowing kernel density estimators, how sort of not very satisfactory the histograms look after that? Would you all agree?
Yes.
Right? It's not informative. Surely this jaggedness doesn't make sense. So let's do the one-dimensional density estimators. We do this. There's a bit of code, nothing magical here. All I do is for every features, these are the numerical features: miles per gallon, the displacement, the horsepower, the weight, the acceleration. So I create a kernel density estimators for all of them. And this is informative. It shows how it varies. For example, do you see that one quality? Let's look at the lower post. What does it tell you? It tells you that it's bimodal distribution. Do you see that there is big hill and there is a small hill here?
Yeah.
Right? So this is the hill of people, rational people buying rational cars, not high horsepower cars. Right? And this little hill is the car enthusiasts, the sports cars and so forth, people who buy high horsepower vehicles. Well, that was the 1970s. Today, these would be considered low horsepower vehicles. This pattern has stayed today. You have the majority of the people buying normal cars and a few people who are into sports cars buying sports cars. Right? As a personal bit, I grew up actually when I was young. Interesting history. I was in graduate school doing my PhD. So a colleague of mine who came from a wealthier background had a nice sports car. So I used to always look at it and salivate. Of course, I didn't have a car at all. So when I graduated and got my first job, my wife insisted that for all the hard work, I should reward myself with a car. I said, fine. And then she picked a sports car. She says, you have always been salivating over a sports car. Here it is. So I got the sports car, and then I got used to the steering of a sports car, the stiff steering and the very tight suspensions and so forth. So after that, an interesting thing happened. If I would sit in a normal sedan, I would just feel uncomfortable, like it's too soft. Okay? So over the years, I've still stayed with sports cars. Okay? Though the age to drive sports cars is probably over, but I still drive it simply because I feel safer in them. Anyway, that's a bit. But you look at the accelerations of them, obviously, again, you see, it used to take 15, 16 seconds before you could go from 0 to 60. Today, you go to 0 to 60 in good cars in 3, 4, 5 seconds. Weight of the car, again, you see most in those days, 2000-ish, 2200 maybe, used to be the most likely car weight. After that, it was a slope downward. So it's informative. You can now group it by origin. And if you group it by origin, you see a very interesting pattern, Let's, for example, look at this. What do you notice? The American cars tend to peak at 18 miles a gallon. The European cars peak at about 27 or whatever miles a gallon. And the Japanese cars used to peak at 30. Already in the 70s, they were giving pretty good mileage, isn't it? Yeah. Say something about the different ways. See, car in US is what somebody is practically. It's a love affair, right? I know that people. I actually know people who celebrate the birthdays of their cars. They're so fond of their car, they celebrate, and they'll always like lovingly wash it and so forth. It's their baby, right? So, well, it shows in the culture. I don't think there are many other cultures that celebrates, where people celebrate the birthday of their car and treat them like the babies of pets. But anyway, look at the weight. And you can see that the weight here is peaking again in US in this location, whereas the Japanese car tends to be light. And when it comes to displacement height, how big the engine is, clearly American cars tend to have bigger engines, more horsepower. So if you look at the mainstream cars of US, they are really not that different from the European and the Japanese, maybe a little bit more horsepower. But this hum that you see of American cars, this big horsepower sports car, you can see that that sort of market is practically absent in other regions. It is sort of there in Japanese also have a love affair with sports cars. So you see a tiny little hump here, another hump here, but obviously they are still not in the same range, what is called high horsepower. For example, in India, what is considered a high horsepower car today? Anybody remembers? I don't know. One of those big SUVs in India, Mahindra or whichever. What's the number of horsepower in those? Anybody wants to quickly Google it up? Yeah, Jeep. Look at the Indian Jeep. No, that is the displacement. CC is the displacement. But you can look up the horsepower. If you Google it, the horsepower of the Jeep in India. Let me know how much it is.
Well, it's saying in India, it's Bentley, Continental. I guess they sell those in India too now.
That is the US one. That of course we shouldn't take. Look at the typical Indian model, which is called a powerful model, like a Jeep.
Mahindra.
Yeah,
Right.
horsepower.
Tata Sumo or Mahindra.
Yeah.
72 horsepower.
How much?
72 horsepower.
72 horsepower. Right. Okay, let's take 72. Let's be generous. Let's make it 100 horsepower. What is the typical horsepower of a muscle car here? Much higher, right? I don't know about other cars, but mine has 610 or something horsepower. So the definitions are different and it shows up in this histogram. So anyway, what is the point that I'm trying to make? Not to brag about my car or this car, because I know that many cars have even more, 700, 800 horsepower these days. I'm told those are called getaway cars from US. So this is what it shows is these density estimators are great vehicles to tell a story about the data, isn't it? They're excellent means. They surface what the data is trying to tell you. These density estimators surface that very well. Would you agree?
Yes.
So yeah. So with that, let's move forward. And look. And by the way, I haven't done it in other Plotly, etc., etc. You can do that. I'll leave that as an exercise for you. In Plotly, here it is called KG plot. In Plotly, it would be called dist plot, DIST. Almost identical syntax. Yeah, similar syntax.
Like the y-axis, if you go back, you show the height and probability distribution for the weight one, right?
The main one.
Weight. Yeah. So why is it like that? Y-axis is 0.00025 versus if you look at the other ones, it's 0.00.
No. The reason is that look at the weight scale. The weight is the range of the data is vast, from 1,000 to 6,000. So you have to spread the sand far and wide, right? If you think of it as a bucket of sand, right? So at any given place, the height of the sand will be very tiny because you have a mile of x-axis to spread the sand. That's it.
So,
if you
in this,
normalize the data, sorry, 1 second. If you normalize the data, then it would be a different story. Please go ahead. Somebody's asking a question.
I was just saying that it is low because the total area for that y-axis times the x-axis has to be 1.
Exactly.
Right?
That is
so
it.
that is why the y-axis is so
That
much
is-
smaller, given the x-axis
Absolutely.
is so much bigger.
Absolutely the same thing. So that's what I'm saying. You have only one bucket of sand. You need to spread it out. If your x-axis is a mile long, then you can't go very high.
But I did that calculation. It doesn't come to 1.
No, it will come to 1.
It will come to 1
Definitely.
because it's like in the third digit, like 10002.
Yeah, you do that. You can do that. Actually, you know that you can actually do the math because each of these kernel density functions, if you use the kernel density of the scikit-learn, you get a function. So you can literally integrate it. Use the SciPy to use the integral function and integrate across the range, you will get 1. You'll get not exactly 1, you'll get up to 4-5 decimal places 1.
I have one question, Asif, before you
Yes.
progress. So the histogram and these kernel density plots, right? They are related to each other, I would assume.
I would consider this the histogram, the poor man's kernel density estimator. I mean, poor man's density estimator and kernel density estimator to be the thing. In fact, my general feeling is I tend to draw the histograms simply because it's a ceremony to draw histograms. But I tend to primarily focus when I'm deriving intuition into data. I primarily focus on the density estimators, the kernel density estimators.
So if the width of the bin goes down to 0, as the width of the bin goes down to 0, it would become a kernel density estimator instead of a histogram.
Yeah, the problem that
Normalized.
In the asymptotic limit of data size going to infinity and the bin size going to 0, it becomes the kernel density estimator, not this Gaussian kernel. So there is an argument. So they see, okay, here's the thing. There are some subtleties. If you take the asymptotic limit, will it become the same as the kernel density estimator? That is called the there's a whole paper on it that says it's a naive way of looking at it and so forth. But broadly, the intuition is correct, but there's some subtlety there. There's a little bit of a subtlety there for why it isn't exactly kosher.
Okay, thank you.
If I remember, I've forgotten the full argument, but there is something there. But your intuition is correct. Imagine that the data set tends to infinity and the bin size tends to 0. What do you get? It will be a pretty good approximation. In realistic terms, right, it's a pretty good approximation. Let us go validate it out. See, here is how where is the histogram? Yeah, look at this histogram. This histogram pretty much looks like the kernel density estimator that we later discover, isn't it?
Mm-hmm.
Right. So this is the histogram in which we have increased the bin size to 500. So it's beginning to take the shape. The trouble is, in reality, because data sets are finite, this begins to get choppy. You see that how the lines are getting choppy?
Yeah.
Right? So that is what kicks in. So you have to assume that the data set size itself is tending to infinity. And the values, the number of bin system, which is 0. I mean, the size of the bin system. So you got that intuition. So there we go. And now I normalize histogram. We did 1D. 1D is beautiful. Can we generalize this idea to 2 dimensions? So for example, if we look at the feature subspace in which we take 2 variables, let's say horsepower and miles per gallon, we're just looking at how miles per gallon and horsepower are related. And we have data points. We project all the data points. And at every point that you find data, you again create a sample. Not this time a genuine sample. How will it look? It turns out you don't have to do much. You can literally, the same code will help you do this. Pick a good color scheme. Here I chose plasma to show the red hot areas, the really dense areas. Now, those of you who are familiar with DenQ would realize that these are your attractants. They're glowing hot, they're glowing yellow. These are your peaks of the hills. So do you see, guys, that this gives you some intuition, a very crucial intuition into the data. Do you agree? Right? And these curves that you see in there, these are called the contour curves. Contour curves are curves of equal density. Right? So at all points along each of these curves will have the same kernel density estimates or values. And so you can see how the data is spread out. If you only want to see the curves, the contour curves, you can, all you have to do is set fill is equal to false, and then you would see that. Also, how many levels, how many curves do you going to see? You can set levels. You control with the number of, so these are minor technicalities in how to use the API. So this is it. Right? Now you can say that, all right, why did we choose miles per gallon versus horsepower? What about other variables? I have 5 variables. So I have 10 possible pair plots, right? 5C2, 5 combination 2 is 10. So how can I see all of them together? surely I don't want to write code one by one, keep drawing it out, create a giant macro. It turns out that Seaborn, Seaborn in particular, this is one of its strengths. It gives you something called a pair plot. And first, let me show you what it does. I'll just shrink the size a little bit. Do you see that in a single visualization, you can get all of them, right? What are the properties I'm looking at? Okay. Do you notice that you get all of them? Look at the diagonal. What is the diagonal? The histogram. What is the top diagonal area? It is the scatter plot. If you look at the subspace of one feature versus another feature, what is the scattering of the data in that space? Already when you look at it, you can see the shape like this, right? For example, here. So what do you expect? You expect the same shape to reflect in the kernel density plot. Here, kernel density plot, I've drawn it out, right? And the lower half are kernel density plot. I find that these pair plots are very informative. I hope you would agree that if you can draw out this pair plots. Now, the code to do that is straightforward. And in the paucity of time, I will explain and not make you do it. Look at this. You create a pair plot in which all you say is, okay, what is the data? Here, I have reduced to the numerical piece, only the numerical columns of the data. Then I say that in the fig, map the diagonal to a histogram. Are we seeing a histogram in the top, in the diagonal? Then you say in the upper part of this, here, put the scatter plots. Scatter plot is also something we are familiar with. And in the lower part, put KDE plots. KDE plots, kernel density estimation plots, we just learned about. And so it will draw all of it together for you beautifully. And you get this visual. Do you see this code, guys? Now, does it look simple? When you see this here, the reality here, does it make sense?
Yeah.
That is it. It's a very powerful way of visualizing this. And I think this is one of the remarkable things about Seaborn, that you could do it so easily. And of course, if you want to break it out by the categorical, say, origin, you can do that. You can say, no, it will tell you more about it. So here it is broken out by origin. So all you had to do is add one more line here, say hue. No, color it by origin. So Seaborn uses the word hue for color. You're saying hue, which is a synonym of color. You say hue is origin. And so you get this beautiful visualization. Right? So I will, and with that, I'll end the kernel density estimators, guys. We will take a 10 minutes break and then we'll learn a completely new topic. Maps. How to visualize data, geographical data, geoplots. And then we'll do networks. So, and then we'll do presentations. And I hope all of you have had your project presentations. This batch has been extraordinarily quiet. I don't know how many of you have done any project at all with data, but we'll find out. 10 minutes break and no more. It is 3:44. At 3:55, promptly I will start.